This is our video for Unit 8, Day 7. What we're going to do today is actually go back to something we talked about in the first unit. We were doing probability, and that's the binomial theorem. We're going to talk a little more, instead of about probability, about using the binomial theorem to expand binomial expressions. So first, give you a couple definitions. Say binomial expression, what we mean is any expression with this form, binomial, so two terms, and then raised to a power, an integer power. So that's what we mean by binomial expression. And the expansion of a binomial expression, a binomial expansion, is when we actually multiply this out. So we'd have our coefficients. So our different coefficients are different powers for A and B, and we have it multiplied all the way out and simplified. So expansion, right, just means multiplied out. So obviously to multiply something like if n was 10, it'd be very difficult to actually multiply a binomial 10 times by itself and actually write all that out. So this theorem is a simpler way of doing that without actually multiplying out. And there's two parts to finding the expansion. So one part is finding the coefficients. So what numbers come before every term? These are called binomial coefficients, and there's a formula for those we'll go over. So there's a formula that'll be on the next page. And the other part is the powers for A and B. Right, by powers, I mean the exponents. So we can use this theorem, this formula, as a shortcut for expanding an expression, a binomial expression, without having to actually multiply it out however many times. So binomial coefficients, again, we talked about this in the first unit. We have this special notation for binomial coefficients, n above r. That's the way you say that, n above r. And that represents a binomial coefficient. Another notation you'll see that means the same thing, it's used sometimes in a different context, is in CR, written like that. But those both mean the same thing. It's important to note here for all of these that n is always greater than or equal to r. And we'll explain what n and r both mean as we work through some problems. So our formula for actually evaluating n above r, and this is why we work with factorials on the second day of this unit. This involves factorials. It's n factorial over r factorial, and n minus r factorial. So just like any time we work with factorials and fractions, we're going to have a lot of cancellation happen here. So that's why it's important to be able to work with those factorials. That's our expression. That's how we find coefficients for the different terms in a binomial expansion. So what do n and r actually stand for? N is the power of the binomial term. So n is the number we're actually raising the binomial up to. So if we had an example, a plus b to the 7th, we are expanding that as 7th power. That would be our n. And then r is 1 less than the term number. 1 less than the term number. So for the first term, in the expansion, for example, r would be 0. For the second term, r would be 1. For the third term, r would be 2, and it keep going on like that. So r is always 1 less than the term number. So we'll do 2 examples here where we actually evaluate binomial coefficients just for some practice. So first we'll evaluate is 3 above 0. So anytime you start a binomial expansion, the first coefficient you'll start with will be whatever your power is n above 0 will go for the first term. Um, so we use the formula, so it's n factorial, so here n is 3, over r factorial, so that's 0 factorial, and then n minus r factorial, so 3 minus 0 factorial. So one thing to remember here from what we've been doing in class is 0 factorial, by definition, is 1. So this is 3 factorial over 1 times 3 minus 0 is 3. 3 factorial, so that's just 3 factorial. 3 factorial, so that's just 1. So in other words, in a third degree binomial expansion, the first coefficient would be 1. I'll do second example, evaluate 9 above 3. So again, we just work this the same way with the formula. It would be 9 factorial over 3 factorial, 9 minus 3 factorial. So we start simplifying. 9 minus 3 would be 6. We have 9 factorial, 3 factorial, 6 factorial. Remember, we can't combine the factorials. 3 factorial times 6 factorial does not make 18 factorial. So we have to evaluate these separately. So this is going to be 9 times 8 times 7 times 6 factorial. The same way we worked with the factorials on day 2. We're going to write them out so we can cancel. So here's our cancellation here. We cancel out the 6 factorial. I have 9 times 8 times 7 over 3 factorial, which is 3 times 2 times 1. And some more cancellation. 9 over 3 is 3 over 1. 8 over 2 is 4 over 1. So I just have 3 times 4 times 7 left over. That's 12 times 7 is 84. Alright, so this would be the fourth coefficient in a ninth degree binomial expansion. So that's just some practice using that formula. And the second part of the expansion is figuring out the powers for a and b, what exponents go in there. So anytime we have something that looks like a plus b to the n, we're always going to start our first term in that expansion would be a to the n, b to the 0. And then from there, As we go to each next term, the powers for A decrease by 1, and the powers for B decrease by 1. So go A to the n, then down to n minus 1, n minus 2, and keep going down because there's no more powers of A left. B will start at b to the 0, move up to b, then b squared, b to the third, until it gets up to b to the n. So the general form of the expansion, using um, the notation from our theorem, would look like this. We use notation for the coefficients. It look like this. N above 0, a to the n, plus n above 1, a to the n minus 1b, plus n above 2, a to the n minus 2, b squared, and then we keep going until we got to n above n, b to the n. So another thing you can notice from this expansion is that the r value in the binomial coefficient for each term always indicates the power of b. So we have 0, we have b to the 0, we have 1, we have b to the first, we have 2, we have b squared all the way to the end where we have n, we have b to the n. So that's the way to help you figure out r, which term number is at the power of b, and r will always match. That's always one less than the term number. So last thing we're going to do is we're going to do one example of a full expansion, and then we're going to go through how you find an individual term in expansion without having to actually expand the whole thing out. So first one, we're going to expand 2x minus y to the fifth. So one thing to note here is the form that these binomial expressions have to be in. They're always written as a plus b to the n. So we have to rewrite this as 2x plus negative y to the fifth. So our a term is 2x and our b term is a negative y. And again, so there's going to be two parts to this. The first part will be finding the coefficients. So our first term would have coefficient here in is 5. So our first coefficient will have 5 above 0, 5 above 1, 5 above 2, 5 above 3, and 4, and then all the way down to 5. And here we're just going to be using that same formula we used before, so n factorial over r factorial, n minus r factorial. So that's 5 factorial over 0 factorial, and 5 minus 0 factorial. But just like before, the 0 coefficient will cancel out, just be 5 factorial over 5 factorial, which will be 1. Another thing, notice is symmetry with these coefficients. This coefficient will be the same as this last coefficient. If I were to plug this in, I would get 5 factorial over 5 factorial, and then 5 minus 5 factorial, which would be 5 factorial, 5 factorial, 0 factorial, which would be the same thing. Right, and that symmetry is going to be true for all of these. Coefficients in here, because we take the 2, subtract that from 5, that'll be 3 factorial. That'll make it the same as a 3 factorial in the next coefficient. Same thing for when we subtract 1 from 5, will give us a 4 factorial, which will make it the same as when we have the 4 factorial and the 5 above 4 coefficient. So we only need to actually evaluate 3 of these. This one, same formula. It's going to be 5 factorial, 1 factorial, 4 factorial. So 1 factorial is just 1. We can go ahead and get rid of that. We have 5 times 4 factorial over 4 factorial. Those cancel out, and I have 5. And this next one will be the last one we need to evaluate. 5 factorial over 2 factorial and 5 minus 2 factorial. That'll be 5 factorial, 2 factorial, 3 factorial. Again, writing it out for the cancellation, 5 times 4 times the 3 factorial, 2 factorial, 3 factorial, and we cancel out the 3 factorials. 2 factorial is just 2, so what I have is 5 times 4 over 2. That's 20 over 2, which is 10. That's the same as the 5 above 3. So now we have our coefficients. The next thing is to figure out the powers. So our first term would have a to the n. So here that's going to be 2x to the 5th. And every term after that, we're going to take the powers of a down by 1 and increase the powers of b. So our next term would be a to the n minus 1 b, which would be 2x to the 4th negative y. Then next we would have 2x to the 3rd negative y squared, 2x squared negative y to the 3rd, 2x negative y to the 4th, and then last we would just have negative y to the 5th. So now we'll go ahead and write out the full expansion with the coefficients and the terms in there, and then we will simplify it at the end. So starting off with our first coefficient, so this is 2x minus y to the 5th. So our first coefficient is 1, and our first power term is 2x to the 5th, right, which we can simplify. 2x to the 5th, that's 2 to the 5th, and x to the 5th, that's going to be 32x to the 5th. Next term, our coefficient is 5, 2x to the 4th, and negative y. So again, we can simplify that. The negative from the y will come out front. 2 to the 4th would be 16, and then 16 times 5 would be 80. The next term coefficient would be 10, and then the power piece, I'd have 2x to the 3rd negative y squared. So negative y squared would just be Positive y to the third is 8. 8 times 10 is 80, so I'll have 80 x to the third y squared. The next term will also have coefficient 10. Powers will be 2x squared negative y to the third. So negative y to the third will be a negative. 2 squared is 4 times 10 would be 40, so I'll have minus 40 x squared y to the third. Then two more terms. The next term coefficient would be 5, and the power piece would be 2x to the first negative y to the fourth. So negative y to the fourth would be a positive, and then 5 times 2 makes 10 x y to the fourth. And then my last term is just that negative y to the fifth with coefficient 1, which just be negative y to the fifth. So that's a full expansion. We're actually writing the entire thing out. And again, this process using this theorem makes it a little bit quicker than actually having to multiply that binomial out by hand 5 times and combine like terms and all that stuff. Last thing we're going to do is just um, go through how we would find a particular term in a binomial expansion. So here's an example. We want to find the fourth term in the expansion of this 3x plus 2y to the 7th. Alright, so if we're finding the fourth term, that means our r is going to be 3. Our r is always one less than the term number. Then in terms of the powers, we'd start with 3x to the 7th, then 3x to the 6th, 2y, 3x to the 5th, 2y squared, and then our fourth term would be 3x to the 4th, and 2y to the 3rd. Another helpful piece with these exponents, you notice that on every term they add up to 7. That's another piece that can help you figure out what the power should be. So we have our powers, it'll be 3x to the 4th, 2y to the 3rd, and what we need is our binomial coefficient here, 7 above 3. So we'll evaluate that over here on the left, 7 above 3, use the formula. And again, anytime we're using factorials, you want to write this out so we can have some cancellations. So 7 times 6 times 5 times a 4 factorial, same 2 on the bottom. There's some cancellation. Right, 3 factorial is 6, so that will cancel out right here. I'm just left with 7 times 5, so that's going to be 35. So that's 35 times 3x to the 4th, 2y to the 3rd, and we can keep simplifying. 35, 3 to the 4th is 81, and 2 to the 3rd is 8. can multiply our 35 by 81 by 8, and we'll get big number 22,680. X to the fourth, y to the third. So that'd be an example of finding one term in the expansion without finding the full expansion. If you want to find some more resources on this or find another video, you can search for binomial theorem or binomial expansion.